Hello everyone, my name is Lizzie, and this is going to be my first YouTube video posted onto YouTube, and I'm going to be going over an organic chemistry 2 topic, specifically electrophilic addition of a conjugated diene. So your conjugated diene is going to be this little one right here. And what does it mean? Conjugated means that there's a double bond directly adjacent to another double bond, and it's a diene because there's two double bonds, right? That's generally what it means. An electrophilic addition meaning that your diene, your diene is going to be attacking this hydrogen, right? That's exactly what's going to happen in this one. So let's go through the mechanism behind this. Now, you see that there's two double bonds. It means that these double bonds can attack in two different positions. Well, let's say it attacks in this position. And my drawings are terrible, but let's say the hydrogen adds here, and you have that positively formed carbocation intermediate right there. Or let's say if it attaches on the tri-substituted carbon right there, you have a positively charged primary carbocation right there. Generally, you're going to want your hydrogens to attach on either end of the conjugated diene because it's going to be the most stable, and you're going to end up with the most stable resonance intermediate. But we can also see this here. So if we perform a resonance structure for this one right here, and let's say this bond moves right here, and it forms this, right? So resonance can totally happen within this molecule right here. Well, let's look at this one. Can you move this double bond here? Well, you can't, because this bond, this carbon, is already attached to 4 different bonds, and if you put that double bond there, it's going to break the octet rule. So you can't do resonance with this. So this is not favorable at all, especially in electrophilic additions to these dienes when forming these carbocation intermediates. Well, let's say now that the hydrogen is being attacked on the other bond, because let's just do both ways just to see the products here. So let's say that this hydrogen adds right here. You have that positive charge there, boom. Or the hydrogen adds here, a positive charge goes there. Well, this is going to be the same issue with this problem. This compound right here. Can you have resonance with this one? Well, you can, because this bond can move here, and it can form the resonance like this. Okay, that is totally possible. What about here? Well, if you put this double bond here, this carbon is going to break the octet rule, and it just won't allow it. So there's no resonance with this one. Just like in this one, there is absolutely no resonance. So you have 2 ways this reaction can take place. It can be from this, or it can be this one right here. Okay, we're gonna draw the resonance for this one. See, this moves there, that becomes positively charged, and let's draw that hydrogen in for simplicity. Okay, so that is what you're left with. Well, now how do you know which of these is the most stable, or going to give you the most stable product, or going to give you the major product, minor product? Now you have to look at the substitution of this carbocations. What I mean substitution, is it primary, secondary, or tertiary carbocation? Is it connected to 3 carbons, 2 carbons, or 1 carbon? If you look at this one, this carbon right here is attached to 1 carbon, 2 carbon, 3 carbon. So it is going to be tertiary, positively charged carbocation right there. And this one right here, you have attachment here and attachment here. This is going to be your secondary. We're going to do the same thing for this molecule right here. This is going to be a secondary, and for this one, it is only going to be primary because it's only attached to 1 carbon. Like I said before, when doing these intermediate resonance structures, you want it to be the most stable. And the most stable is going to be your most substituted carbocation intermediate. And in this case, we're dealing with a tertiary, a secondary, and a tertiary, and a primary. This one is definitely more stable than this one. And when I mean stable, I mean that there is a lower energy required for this reaction to proceed, and it's going to be more reactive. So the product is going to be more favored and likely to have a greater yield than of these products right here. All right, now that we've decided that these resonance structures are a lot more stable and a lot more favored, we can move on to adding that bromine back. That diene is going to attack that bromide and form the structure here. Similarly with the other resonance structure. I'm writing in the hydrogen just for a future purpose. You're going to know right now. Okay, and then that is going to attack here. Perfect. And what you're left with is this. Now, how do you know which one is your thermo or your kinetic product? Well, your thermal product is going to be the one where the alkene is the most substituted. And same thing with the carbocation intermediate, your most substituted is generally going to be your most stable and therefore your thermal product. So looking at this compound right here, we notice that the alkene is attached to 1 carbon, 2 carbon, and 3 carbon. This is a tertiary substituted alkene, which means it is going to be your stable thermal product. But we can also see it from this side as well. This alkene is connected to 1 and 2 carbon. It is a secondary substituted alkene. So since 3 is greater than 2, this is likely to be your thermal product 90% of the time. Or 99% of the time, because this is your thermal product. But we can also count the distance between the hydrogen and the bromide added. So 1, 2, 3, 4. Also to remember that thermal products could happen in the 1,4 addition. And this one, in this case, it is your thermal product. So not only is it the most stable, the alkene is the most substituted. And when looking for the product of a thermal or a kinetic, you're always going to look at this. Is the alkene most substituted or least substituted? The most substituted alkene is going to be your thermal product. And now let's look at this compound right here. Okay, this is a result from, the carbon, hydrogen is 1, 2 distant away. That is going to be your kinetic product. Cool. So it is not the most stable, but it is your fastest producing product. Because it has the lowest activation energy. And it is also faster in reversing. Yeah, so this is kind of the mechanism behind how to do an electrophilic addition of conjugated dienes and when to know which one is your thermokinetic product. Yeah, this was my first video, so it's a little choppy, but the future videos I'm going to get a lot better at explaining this, and it's going to be a lot more simplistic than these little terrible drawings that I'm doing. Yeah, but just to wrap this up, remember your thermal product, again, is going to be your most substituted alkene. It could resolve in the 1,4 addition, not always a time, not always, it won't always result in the 1,4 addition. However, again, your thermal product is going to be most stable. Your kinetic product happens the fastest. It also is favorable in lower temps and thermo in higher temps. Dope. Yeah, give this a like if this helped you even a little bit. And let me know any suggestions you guys have for future videos. The next video I will be doing is going to be doing other examples of electrophilic addition of conjugated dienes so that you have a greater idea of what's going on. All right, like and subscribe.